Hi everyone, this is week 11. This week we will cover how to compute volumes of three-dimensional objects obtained by rotating some regions and how to use integrals to compute such volumes, okay? So let's look at the first example. You see a three-dimensional object here, right? And here you also see the cross-sections, which are rectangles like this. Now, our aim is to compute the volume of these three-dimensional objects by using these cross-sections. How can we do that? So the idea here is you should imagine that you slice this three-dimensional object into rectangles like that. So you slice it into rectangles so that you have infinitely many rectangles to cover the whole volume, okay? This is the idea. So to compute the volume, we need to use the area of this cross-section. This is the cross-section. We need to imagine that we slice these three-dimensional objects into rectangles like that. So the volume here is computed by an integral. If you integrate the area of that cross-section, okay, let me denote the area of that cross-section as a of x. If you integrate that area through x-axis from 0 to 3, these are the boundaries on x-axis, right? You need to look at the interval over which your three-dimensional object lies. So the boundaries of the integral will be from 0 to 3, of course. Why we obtain the volume of the whole three-dimensional object if we integrate a of x from 0 to 3? What is the idea behind this integration to obtain the volume? So the idea is integral is a continuous summation. As I always tell you, integral is a continuous summation. By putting a of x inside the integral, in fact, you are summing up the areas of all those rectangles. You know, I draw rectangles at the beginning. So consider all those infinitely many rectangles who has areas as a of x. By integrating them from 0 to 3, you in fact sum up all those a of x's, okay? And that in that way you cover the whole volume. This is the idea. Any question about this idea? Okay, then let's try to express a of x in terms of x. Look at this point, please. And the components of this point is given here. You see, it is the point x. So this point is the x point on x-axis, and the y component of this point is already given like that. So minus 9 minus x squared. Also, there is this corresponding point on the other side, right? So look at the y component of it. And similarly, since this is the positive y axis, it will be the same expression with positive sign. Okay, so what we have done, we need to express the area of this rectangle, right? Since we have 45 degrees here, this length is x, that's why this length is also x. The height is x. And what about the base of this rectangle? Base is from here to here. So it is this length, I mean this part plus this part. So that this part has the length of 2 times, I mean it is already given, but I was trying to explain this length. So this is the base length and we also the height. So the area of the rectangle is 2 times square root 9 minus x squared times x, of course, which is the height. So this is the base and this corresponds to the height. And then we just need to insert this here inside the integral to compute the volume, okay? So it goes like 2 times 9 minus x squared square root x dx. And how do you compute this integral? By using substitution, of course. If this is u, 9 minus x squared, what is du? Take the first derivative. Then x dx is in fact, this part is in fact minus du over 2, right? That's why the integral becomes, is this minus 2 square root of u times this part is minus du over 2. I send minus out, and then you can simplify, and you also need to transform the boundaries. You cannot directly put from 0 to 3 here. No, these are the boundaries for x. Instead, you need to compute the boundaries for u. If x is 0, u is 9. If x is 3, u becomes 0. So the new boundaries are from 9 to 0. Let's quickly compute this integral. It is minus, this is a power function, u to the power 1 to 1/2. So add 1 to the power, divide by the same power. And then you can safely insert the boundaries for u like that. If you insert 0, you will obtain 0, of course. Minus, there is another minus here, so plus. Now insert 9. So this positive real number gives you the volume of this three-dimensional object, okay? And how do we compute the volume here? By slicing this three-dimensional object into rectangles like that. So like these rectangles, we slice it. We put infinitely many rectangles to cover everywhere. And then we concentrate on one of the rectangles, find the area of it. Integrating the area means that integration is a continuous summation. That's why integrating this area means that you are summing up the areas of all those infinitely many rectangles. That's why you cover the full volume, okay? So this is how you can compute volumes by slicing your objects. We used vertical slice here. Okay, if no questions about this example, I want to move on. So let's move on. Next example is like that. This time, our slices are isosceles right triangles, meaning that we have a triangle here, right? This is a right triangle, and isosceles means the lengths are equal. Okay, then what is the idea here? Let me again try to draw it. Maybe I can draw it here for you to see better. Okay, so how do we compute the volume? What kind of three-dimensional object we are interested in here? It is a bit hard to draw, sorry. Let me try again. So, yes, I will be inserting infinitely many triangles like that, okay? Like this one, and this one here. So, can you imagine? In total, if you put all those triangles over the given base, try to imagine that you have infinitely many such triangles. So in total, you obtain a three-dimensional object, right? And now I want to find the volume of this three-dimensional object by integrating the areas of such triangles. Okay, let's concentrate on one of them. Now, my aim is to find the area of this isosceles triangle. So let's denote it by A of X or Y. Okay, let me first explain that. So volume will be obtained by integrating the area with respect to dy or dx. We need to first decide this. And this is not something difficult to decide. You just look at the picture and you try to see towards which axis your cross sections are moving, towards which axis your cross sections are constructed. So they are triangles like that, and they are constructed over y-axis, right? That's why you will choose dy here. That's very crucial point to decide. You need to choose dy because you see in the picture that cross sections are constructed through y-axis. Okay, after deciding that, let me clean my picture. Okay, so we understand that the integral should be dy. Then you understand that you need to express your area in terms of y. Okay, and then after you decide this, it is easy to do the computation because now this length and this length should be found in terms of y. Look at the curve given. Okay, now I want you to concentrate on this point. This is a point on the curve, and let's try to find out the x component of this point, okay? Okay, like this. So this means that you need to solve y in terms of x from the given equation because, you know, I just named this point as an arbitrary y. So let's solve x from the given equation of the curve in terms of y. What is it? It is 1 minus y squared square root plus minus, right? Plus minus. So since this is the positive part of x component, x-axis, this point, this x hitting point is in fact plus 1 minus y squared square root. And also there is also the corresponding point on the other side. And it is x component will be similarly, this will given by the same expression, but with a negative sign in front because this is the negative part of the x-axis, okay? So then I think I have the length of this part, right? It is this, and I mean 2 times this, in fact, 2 times 1 minus y squared square root. And since this is an isosceles triangle, the height is also given by the same expression. And then we are ready to express the area in terms of y. Let's do that. Area of this triangle is 1/2 base times height, right? High school information. So it is 1/2, base is 2 times 1 minus y squared, and height is the same, 2 times 1 minus y squared. So after doing the simplifications, you can just insert it to here. Now, what about the boundaries of your integral? Since we are integrating with respect to y, you need to look at the y boundaries. You need to look at the region and try to see the y boundaries of your region. So since this is a circle of radius 1, you know, x squared plus y squared equals 1 is a circle of radius 1. So this is plus 1 and this is minus 1. These are the boundaries of y-axis, on y-axis. So let's write one more line. A of y, as we computed here, is 1/2, 2 times the base times the height, dy, and then minus 1 to plus 1, okay? I think after doing simplification and multiplication, this will be a very simple integral to compute. Power functions you will obtain and you can easily compute them. Okay? So let me write it like that. It is 2 times 1 minus y squared dy integral from minus 1 to plus 1. Okay? So I will leave the computation to you. This is an easy integral. We have lots of things to cover today, so I need to save some time. Any questions now? These are the y boundaries. Any questions? Okay, so let's move on. This is a very similar question. That's why I want to skip it. I want to concentrate on nicer examples. But this is will be a nice exercise for you. Okay, now we have more volumes to compute by integral, but before solving these 2 examples, I want to construct a diagram for you, summarizing this method, Boischer method, and cylindrical shells method. These 3 techniques are the main techniques that we use, and you will be having examples on your homework on those 3 techniques. So let me construct a diagram that summarizes everything for you. Volume of solid objects obtained by rotating a region, a given region, around x-axis or y-axis, or y-axis, or around some line, it doesn't matter. Okay, you will see, you can also rotate around different lines. So this is the title. I can show you 3 different methods to compute such volumes. First, disk method. Second, Voischer method. You will see in a minute that these 2 methods are so similar. They are almost the same, but the last technique is totally different than the first 2, cylindrical shell method. Okay. So what about disk method? Let me give you some more details on disk method. To cover the whole volume, you will be slicing your 3-dimensional object, and those slices will be disks, okay? Those slices will be disks, and you will be using the area of the disk. A of x will be the area of disk in the first case. So you will be integrating a of x dx over some interval in this case, where a of x is an area of disk. So it is given by pi r of x squared. Pi r squared is the area of disk, right? Where r of x is the radius. The setting can be also in terms of y. I wrote the setting in terms of x, but it can also be symmetric, like in terms of y too. In Voischer method, you will be using not the whole disks, but rings. There will be an empty hole inside. So you will be using rings. A of x, in this case, will be the area of the ring. So how do you compute the area of such a ring? There is an inner radius here, right? R inner. And there is an outer radius. Bigger radius and smaller radius, I mean. So to compute the area of that ring, you will, of course, do this. R outer square minus R inner square. This will give you the area of the ring. And you will be integrating this to compute the whole volume from, I don't know, A to B, let's right? I again warn you, the situation can be also with respect to Y. But for the cylindrical shell technique, you are not slicing your 3-dimensional object anymore. You will be using a totally different idea. We will use cylindrical shells. So let's consider a very thin cylindrical shell like that, which has radius r and height h. So let's consider that you cut this cylindrical shell, you cut it up. So, you know, the diameter here is what? 2 pi r, that will correspond to here if you cut it up. H is again h, it is at the same place. So we will be using the surface area of this cylindrical shell. In this case, A of x will be the surface area given here. So it is 2 pi r base times h, of course, and to compute the volume, you will integrate this surface area, 2 pi r. Okay. Yeah, okay, 2 pi r, 8 dx or dy. It will depend on the question, but now I will write in terms of dx. Okay, so this diagram summarizes the methods in a general shape. Okay, there are all, of course, more details in each technique. I will show the details while solving the example. Okay, so after having this quick summary, let's look at these two examples where we will be using this method to compute the volume. Okay, this method will be used here. Okay, let's start with this one. So the question is, we are given a region here, blue region, and we will rotate this region around x-axis. It is given like that. And we want to compute the resulting volume. What kind of object we will obtain after we rotate? So something like this, right? Like that. So now I will slice this three-dimensional object into cross sections. And the cross sections here are discs. Let me show you by drawing. Okay. I cannot draw. Let me try once more. Now it looks better. Okay. I slice the object vertically. So the slices are full discs, right? These are the slices after I rotated. Now, to compute the volume, the idea is, let's say, the idea is to integrate the area of this disk with respect to dx or dy. What do you think? Which one? So these disks are considered and constructed through x-axis, right? That's why I need to take the integral with respect to dx. So they are sliced through x-axis. I mean, we collect all of them together through x-axis. So the integral should be with respect to x. That's why I need to express the area of this disk in terms of x. So what about the boundaries of x? Look at your region and try to see the boundaries over x-axis. So the boundaries are from 0 to pi over 2 as it is given in the picture. Now, my aim is to find out the radius so that I am able to write the area in terms of x. So radius of this disk is obviously given by this curve. So look at the curve, it will directly be the radius sine x cosine x. So this height, which is the y component of that point, is given by the curve. Okay, then the area of this disk is a of x is pi r of x squared. So that's it. They're almost done. Pi r of x squared dx. So pi, I am just inserting r of x. Sine x cosine x dx. Don't forget to square your radius. Like this, 0 to pi over 2, 0 to pi over 2. Okay, so if you compute this integral, you will find a real number, positive real number, and that real number will give you the area of this the volume of that three-dimensional object. The important thing here is that, first of all, you need to decide the integral should be in terms of dx, right? Because these are vertical slices. They are moving through x-axis. That's why with respect to dx. Then insert your boundaries of x and then try to express the area in terms of x like that by using your curve. That's the key points. Any question? If not, let's look at this example, 17. Now, the given region is rotated around y-axis. After you rotate it, you will obtain a three-dimensional object again, like this, and you will slice it horizontally this time. So let's see the slices. The slices are horizontal disks now. You see? And then we can start computing constructing the volume. Volume is integral of the area of these horizontal disks. Of course, the idea is the same, but is it with respect to dx or dy? Which one? This time, the slices are moving through y-axis, right? Y. So the integral should be with respect to dy. Once you fix this, you can understand that you need to express the area of that, the area of that slide with respect to y. Okay, let me remove those. Okay, so once you fix that, the integral should be with respect to the dy. Area of this disk should be in terms of pi, and then it goes like pi radius square. So here, this is the radius of that given slice, given disk. So we need to express it in terms of y. Can we do that? Yes, we can easily do that. Let's say that this is an arbitrary point y, and now I can find the x hitting point on x-axis for that point. So what is the x component? It is given by this curve, right? So x hitting point is given by the curve tangent pi over 4 pi. You see, this is in fact the radius of our disk. So this part is exactly the same as the radius. So that's it. Let's insert everything. By the way, what are the boundaries of your region on y-axis, y boundaries? They are 0 and 1. So you look at the y-axis for your y boundaries, of course. Okay, let's insert what we have found there. A of A area is pi radius square y. So it is pi radius is expressed in terms of y by the curve tangent pi over 4y. Don't forget to put the square, and then boundaries, of course, 0 to 1, 0 to 1. Okay, so this integral gives you the volume of the three-dimensional object. I won't be computing the integrals today. I will leave that part as an exercise for you. So you see, these two examples shows you, in fact, they summarizes you the disk method. The question will be with respect to x, or the question can be with respect to y. So both stories are explained here. If no questions, I want to move on. Okay, let's move on to the next example. For this group of questions, there is no picture, there is no graph. We need to draw the picture together. Okay, it says find the volumes of the solids generated by revolving the given region about x-axis. Let's do that. So let me draw y equals x cubed first. Y equals x cubed is such a line. Y equals 0 is x-axis, and x equals 2. This is x equals 2 line. And this is the given region. Now, it says that rotate this region around, this is y-axis, I'm sorry. It says that rotate the given region around x-axis. Okay, let me insert some more space. Okay, so we will rotate the given region around x-axis like this to obtain such a, so the rotation axis is like that. So the resulting three-dimensional object will be something like this. And then we will slice this into vertical disks, right? So let's choose an arbitrary point x, and this is our vertical slice, which is a full disk, right? And remember that this curve is y equals x cubed curve. That's why the radius here, radius of this disk is given by the curve. So it is x cubed. So the volume is a of x dx, where you need to use the x boundaries on x-axis. X boundaries is from 0 to 2 because this is x equals 2 line. So what is a of x? A of x is pi radius x squared dx, and we already find out the radius as, okay, let me write the whole integral again. Radius is x cubed, squared dx, put boundaries, and that's it. This is a very simple integral to integrate. Okay, this is x to the power 6. I add 1 to the power, divide by the same power, and then you will obtain the boundaries. So the result is 2 to the 7. So this real number gives you the volume of that three-dimensional object that we consider here. Okay, so let's move on. Any questions? Okay, let's move on. Let's solve one of them. Again, find the volume of the solids generated by revolving the regions around y-axis. This time we will be revolving around y-axis. Let's try this one. X equals square root 5 y squared. This is a parabola, right? We know how to draw parabolas like this. Okay, x equals 0 is y-axis. Y equals -1, y equals 1. Okay, these are the lines. Y equals 1 and y equals -1. So the shaded region is where? The region is described, the region is the region between the given all those curves like that. This is the shaded region. Okay. So we will rotate this region around y-axis like that. What do we obtain? So something like this we will obtain after we do the rotation. A three-dimensional object like this, okay. So I will just shade the region and we will try to imagine what will happen after we rotate it. Something like this will happen. Okay, so how do we slice it? After we rotate it, okay, let me draw the parabola again like this. Okay, so the slices will look like horizontal this time. Slice your picture. They will be horizontal discs in this case, not vertical. But do you see the difference? Here we used these vertical discs and we integrate with respect to x. Now we will be using these horizontal discs and we will integrate with respect to dy, okay? So integral goes like a of y dy, of course, where a of y being the area of that horizontal slice, which is a disc. And the integration on y-axis, the boundaries on y-axis are from here to here, the boundaries of the region. And we know it, we know them as this is the point 1, y equals 1 line, and this is the point -1. So this is the interval of integration from -1 to +1. -1 to +1, because your region lies above -1 to +1 on y-axis. Okay, then the radius of this disk. For some arbitrary point y, this is an arbitrary point y, the radius is determined by this curve, as you can see, right? You need to concentrate on this point on the curve. So we need to find the exiting point, because everything should be expressed in terms of y. Radius also should be written in terms of y. So exiting point, this is the equation of the curve. It is already given by the equation of the curve. It is square root 5. It's square root 5 y squared, which gives us the radius. That's it. We have everything. Construct the integral. Pi r of y square dy. Boundaries are from -1 to +1. Okay, let's insert r of y and then stop. Pi r of y is given by the curve, exiting point of the curve in terms of y. dy, don't forget to put the square, -1 to +1. And let me emphasize that everything is with respect to y, okay? We try to express everything with respect to y, and we used y boundaries of the region. That's it, okay? Any questions? If no questions, before the break, I want to talk a bit on Washer method. Okay, so far we use disks everywhere. Horizontal disks, vertical disks. Now, we will be using rings. Remember what Washer method is about? So, we won't be using full disks anymore. There will be an empty hole inside our disk. So, it is a ring now, not a disk. Okay, let's try to apply this idea. Washer method. Let's start with the first example. You see the shaded region in blue here. It's a big region. And the question is, we will rotate it around x-axis like that. And we will try to compute the resulting volume of the resulting three-dimensional object. So I am rotating it now. Okay, that's fine, I guess. Okay, after you do the rotation, all those parts will be covered during the rotation. And now I will slice this three-dimensional. It is kind of rectangular cube. And you take this ellipsoid inside. Inside part is empty. So this is just a cross-sectional view. It is a three-dimensional object. As I explained, it is kind of a rectangular cube like that. And you take this big ellipsoid inside, in the middle of it, you take it out, this big ellipsoid, okay? So let me slice it into vertical disks. So here I am inserting one of the slices. So I cut it into infinitely many slices like that. Okay, so the slices are now not the whole disks because of the empty part inside. These are rings. And I will try to express the area of this ring in terms of x. Why in terms of x? Because the volume, the integral giving us the volume should be in terms of x, as you can see from the picture, all those rings are moving through both ways, moving through x-axis. That's why the integral will be with respect to x. That's why the area of that ring should be expressed in terms of x. Okay, so this is a ring. That's why it has an inner radius, which is determined by the given curve. So what is inner radius here? Look at the equation of your curve. It is square root of cosine x. And this ring also has an outer radius, right? Which is here. You should really follow me carefully. So outer radius is here. From x-axis to that line. So what is it? And it is determined by this line. What is the equation of that line? It is constant, just 1. Outer radius is always 1. No matter where you draw your disks, here, here, empty part is changing. The size of the empty part is changing, but the outer radius is always same. It is determined by y equals 1 line, right? So outer radius is always 1. That's why it's written 1 here. Okay, we have what inner radius is, what outer radius is. So we are ready to construct the integral. And these are the boundaries of your region over x-axis. Boundaries of x are given by minus pi over 2 to plus, this is pi plus pi over 2, I guess. Okay, what about area? So the area of x is the area of that ring. So pi, our outer square, minus our inner square dx, from minus pi over 2 to pi over 2. What is outer radius? We just discussed that. It is 1. What is inner radius? The blue part is given by the curve, square root of cosine x. Put a square there. Don't forget to square your radiuses like that. And then, yeah, the boundary is minus pi over 2 to pi over 2. The result of this integral will give you the volume of this strange object. Okay? So this is how you apply Washer technique. Washer method, let me emphasize it. We used washer method here because we are using rings. Washer means you are not using full disks, but rings like that. Okay, before the break, let me also explain this example. Okay, let's do it here. Look at this example. Sorry. Look at this example, please. Yes, this time you will rotate it around y-axis. So let me draw it again. You have this shaded region. And then if you rotate it around y-axis, something like this will happen, right? Some three-dimensional object like that you will obtain. Let me draw it bigger. This is too small. Okay. Yeah. Okay, so what we have? We have this region given by a curve. I rotate it around y-axis. And this is what I will obtain after doing the rotation. Now I am ready to slice it. I will use horizontal slides. Okay, these are the cross sections. Be careful, not vertical, but horizontal cross sections will be used. So for an arbitrary y point here, this is our inner radius. Concentrate on this point, please, which is on this curve. And the inner radius is given by exiting point. And this curve is this one, x equals tangent y. That's why this exiting point here is tangent y, which is the inner radius for us, our inner. This part is the inner radius. What about the outer radius? Okay, let me draw it here. Outer, okay, from here to here. So outer radius is this green line, and it is always fixed by this constant line here, right? So what is outer radius? It is 1, always 1, no matter where you draw your, let me show you. So like that, you see, this outer radius is always determined by this line, which is x equals 1 line. So the outer radius, which I indicated by green, is always 1, right? It's always 1. So we are ready to construct the volume, I guess. It is, first of all, the area of the rings. Okay, this is the ring that we use. Let me shade the ring. Okay, this is the corresponding ring. And the rings are moving through y-axis, right? In my picture. That's why everything should be in terms of y. That's why we will be using y boundaries of the region. So you see, these boundaries will be used from 0 to pi over 4. This point is given as pi over 4 in the question. So 0 to pi over 4. And what is a of y? A of y is in fact, okay, let me draw. If you cannot see from the picture what we use there, we use these rings with the outer and inner radius, okay? So from center to here, this is outer radius. From center to there, this is, black one is the inner radius. Our inner given by the curve tangent by the green one is the bigger radius, outer radius, which is always 1. Okay, let's insert them to integral now. Integral is from 0 to pi over 4. Pi, our outer radius minus our inner radius squared dy. So outer radius is 1 minus inner radius is tangent y. Don't forget to put squares dy. Insert your upper lower boundaries for the integral. You see? And this is the y version of washer method. So it depends on the question whether you use x dx or dy. You decide the variable after you work on your picture. If your disks or rings are moving through x coordinate, you use the x. If they are moving through y coordinate, like in the second case we have here, you need to express everything in terms of dy. That's the idea. Okay, that's how you use rings instead of disks to compute the volumes. Any questions? Okay, if no question, I want to stop here for the first part.